Hi everyone, thank you for joining me today. I am Hanine Zakaria from McGill University. And if I tell you that we can combine viruses and magnetic nanoparticles to form a new material, would you believe me? Today, I'll show you how magnetic tuning and the assembly of iron oxide nanoparticles will make this possible. And we're interested in these particles because we can use them in many applications like biomedical applications, magnetic data storage, photoactive applications, catalysis, and wastewater treatment. These particles exist in many phases, but the three main phases are magnetite, megamite, and hematite. And we're particularly interested in the magnetite because of its superior magnetic properties, where it has a high saturation magnetization and high magnetocrystalline.
Seems we're having some technical difficulties. Hopefully we get that sorted soon.
I think I lost my connection. Um, you were able to hear the the lattice structure of the particles?
Yeah, please continue.
Okay, so I was saying that these particles behave as ferromagnetic because the iron 3 in the octahedral and the tetrahedral sides, they align anti-parallel and the spins cancel each other. So the overall magnetization is only coming from the iron 2 in the octahedral sides. And in literature, there are different methods to synthesize these particles, but usually it operates under harsh environment like very high temperature or alkaline medium. However, the one that I'm using is an in-house method that we have developed in the lab, and it operates under a mild condition. I don't know why I can't. Okay, so it's working. Where we mix the sodium oleate, which is the surfactant, with the right ratio of the solvent, and then we add the iron precursors, and we reflux at only 75 degrees Celsius overnight. And the other day we do the purification, and our particles are ready to be used and analyzed. Now we come to the central question. Can we manipulate these particles and tune their magnetic properties? And to answer it, I'm working on two interconnected projects. The first project focuses on modifying the core of these particles by doping them with gadolinium. And the second project shifts more toward an application where we're gonna self-assemble these particles using the tobacco mosaic virus called protein. Let's start with the first project. So doping iron oxide nanoparticles with a small amount of metal can tune their magnetic, optical, electrical properties, and catalytic activity. And among the different metals, we're particularly interested in the GD3+, because as you see here in the electron configuration, GD3+ has 7 unpaired electrons. So we think by introducing it into the lattice of our magnetite, this gonna enhance the overall magnetic response of these particles. And in order to test our hypothesis, I synthesized particles with different GD concentration, and we did a lot of characterization, including the ICP-MS that confirmed the presence of GD in my system, and we obtained experimental percentages close to the theoretical values. Also, we collected TM images that showed that our particles are uniform and it's monodispersed. We collected TGA spectra, and we found that the thermal stability is decreasing with the increase in GD content. And to confirm that what we're actually synthesizing is the magnetite phase, we obtained the XRD spectra, and as you see here, we can locate all the peaks that correspond to the magnetite, and also we collected the IR spectra. Finally, we were able to obtain magnetic data through our collaborator, Professor Moon from SFU University. And because my particles are small and it's super paramagnetic, it's like 4 nanometer in size, we collected the MH curves at two temperatures, the 300 and 2 Kelvin. From the 300 Kelvin, we were able to extrapolate the saturation magnetization. And from the 2 Kelvin, we obtained the remnants, magnetization, and the coercivity, and all the data are summarized in this table. And here's the plot of the MS values versus gadolinium concentration. When we start adding the dopant, there is a decrease in the MS value, then it recovers, then it continues to decrease as we're adding more GD. And MR values follow similar trends. So this is opposite to what we were expecting. And there is a more complicated chemistry that's taking place, and our initial hypothesis turned to be incorrect. Now we're working on understanding this behavior by considering whether it's the ionic size effect or it's the spin effect or simply both of them that are playing a role in this behavior. And we're considering the ionic size effect because GD has a larger ionic radius than iron 3. And we obtained the lattice parameters, and as you can see here, we have a slight change in the lattice constant with different GD concentration. And our preliminary explanation of what's going on is that at low GD concentration, GD will go to the octahedral B sites because it's larger, and this is causing a disruption for the AB super exchange interaction, and we have maybe a ferromagnetic coupling, antiferromagnetic coupling with the iron. And then when we keep adding more GD, this GD will go to the tetrahedral side. So we're recovering some of from the interaction between the A and B sides, and we have less disruption to the system. And to further and understand the ionic size effect, we extended our studies towards two additional trivalent cations, yttrium 3+, which has a comparable size to gadolinium, and scandium 3+, which is significantly smaller, and both of them, they spin 0. And we recently received the data, and we're just start looking at it, but as you can clearly see, the scandium is behaving different than gadolinium and yttrium. Now let's shift focus toward the second project where we're gonna harness the tobacco mosaic virus in order to self-assemble these particles. Tobacco, this virus is one of the very first known viruses, and a lot is known about this virus. It has a unique shape, and it's very stable. And importantly, we can use it without the viral genome, and this is make it safe for practical application. It can self-assemble into different structure depending on the solution condition, where it can form monomers, disk, log disk, or single helix. This is all depends on the pH and the ionic radius of the solution. And we're particularly interested in the disks because of its properties. And our former colleague, the late Dr. Abu Bakr, was able to modify the surface by adding the histidine tags. And then with histidine-histidine interaction, he was able to obtain these nice disk arrays. He mixed it with the gold nanoparticles and was able to obtain a nice hexagonal sheets at pH 6.8. And in my project, we're trying to use these disks, but by using the iron oxide nanoparticles. And then we will obtain these nanorings, and it will be very special because the spin's gonna align in a clockwise or counterclockwise manner instead of pointing up or pointing down. And this will create what is known as the Fluxy closure state. And this is very important, like for data storage applications. So the first step was to do some ligand exchange interaction because to get my particles into the aqueous phase. So I tried two different surfactants, the 3,4-D-HPA and the Tiran. However, the Tiran was more stable, so I'm using it now. And at the beginning, I tried to mix with the discs at a similar condition as the gold nanoparticles, and I was able to obtain few rings, and my particles were dispersed everywhere, which means this condition doesn't work with the iron oxide nanoparticles, and we need to optimize the solution condition by taking into account the buffer, pH, concentration of iron oxide nanoparticles, particle to protein ratio, ionic radius, and the time. And with the help of my summer student, Charlie Debon, we were able to cover a good range of possibilities, and we were able to find the best conditions to obtain these sheets. We used the 100 millimolar potassium phosphate buffer, 0.5 milligrams per milliliter as a concentration of iron oxide nanoparticles, and the best pH was 6.3 and 6.4. And as you can see here, we have two sheets that are stacked on top of each other. So in conclusion, for the first project, we were able to successfully synthesize particles with different GD concentration and to characterize them using different techniques. And for the second project, we did some ligand exchange interaction, and we optimized the self-assembly conditions, and we found that the pH 6.3 and 6.4 are the best to obtain the nicely packed hexagonal sheets. And building on these findings, the next step is to continue to understand the magnetic behavior of these particles by understanding the ionic size effect. Also, we're gonna do some computational chemistry, and we gonna to understand the spin effect using the quantum espresso software. Also, we're gonna collect the X-ray magnetic circular dichroism, some yields measurement, and the FMR measurements. And for the second project, we're gonna characterize these sheets by obtaining the magnetic force microscopy and electron holography. Finally, I would like to thank my supervisor, Dr. Amy Blum, collaborators, and the Blum team, and all the funding agencies who made this work possible. Thank you for listening, and I'll be happy to take any question.
Thank you. Very, very nice talk. I think we have time for one quick question from Akash in the chat. He says, does the difference in the ionic radii change the phase of the ionic nanoparticles? Have you confirmed the phase stability using Raman analysis?
Can you repeat, please, the question?
Yeah, he says
Ionic size effect. Yeah, I got the question about the ionic size effect.
Yep. And he says, have you confirmed the phase stability using Raman analysis?
We tried the Raman one time, but the laser was burning the sample, so it was hard to obtain any spectra.
Gotcha. Okay. Let's thank the speaker again.